Okay, so let's review again what we have so far. The plan is that we have a charge distribution and we want to get the electric field in a different way. And so we've already gone through this before. We found how to get from the charge distribution the potential at every point in space, which is just a number. And we did that for point charges. The potential at a point due to many point charges, you just add the potentials due to each charge. Here we're keeping the reference of potential to be 0 at infinity. And then once you know the potential, you can get the electric field by getting the derivatives as usual. So now we want to extend this to other kinds of charge distributions. We don't just have point charges in space. We can have line charges, volume charges, surface charges. So all these kinds of charge distributions, we need to also find a way to get the potential in space due to these different charge distributions. So what we know is that for point charges, if you want to get the total potential at point P, you just add the potential due to charge 1 at point P, the potential due to charge 2 at point P, and so on, as if all the other charges don't exist. So when you're getting the potential due to charge 1, you're assuming all these don't exist. When you're getting the potential due to charge 2, you're assuming all those don't exist, and so on. So how would we extend that way of thinking to get the potential at a point due to a contour of charge? Well, as usual, whenever you have a continuous charge distribution, you cut it up into small parts because we only know how to deal with point charges. So we can write down the total potential at point P. We can assume that this contour of charge is basically an infinite number of point charges. We have to cut up this into an infinite number of parts because the only thing we know is the potential due to a point charge, which is kq over r. So if you sum k delta q over r for each element of length, so this is the ith element of length, it has a charge delta qi, it has a length delta li, and the distance between the element of charge and point P is rip. If we add the potential due to each one of the elements of charge on the contour and we find the potential at point P due to each element and add them, this will give us the total potential. Now this limit of sums can be written as an integral, and so officially we can write it down this way, where here dq is equal to lambda dl. Okay, what about a surface charge distribution? If you want to get the potential at point P due to a surface charge distribution, how would you do that? Again, you cut up the surface into small elements of area, and then what would you do? You get the potential due to each element of area. For instance, this is the ith element of area. It has area delta AI, it has charge delta QI. The distance between the element and point P is RIP. The potential due to that element only at point P is K delta QI over RIP. Then you sum for all the elements from the first element to the last element, and there are infinite number of elements. We let the area size of each element of area go to 0. This limit of sums can be written as an integral. Get this result. It's the same exactly as before, but instead of dq being lambda dl, it's sigma dA. Of course, you can imagine what the case would be for a volume charge distribution. You cut up your volume into small elements of volume. You get the potential due to each element of volume. You let the size of each element of volume go to 0. And this summation can be written as an integration. And instead of dq, now we take dq to be rho dv.